This video is a speed run of problems 15 to 19 on the AMC 10B. Let's start with problem 15. What is the least positive integer m such that m times 2 factorial times 3 factorial times 4 factorial times 5 factorial times 16 factorial, and it's ... here is a perfect square. And we're trying to minimize m. And the answer choices are sort of jumbled up, but here they are. So, let's see. Well, how many times does 2 appear in that mess of factorials? So it appears once in every single one of these. But how many of these are there? So there's 16 minus 2 plus 1, which is 15 2's. So we need one more to make there a perfect even number of 2's, which is going to be a perfect square, because we need an even number of every exponent. So we know that this number must have a factor of 2. Does it have to have a factor of 3? Let's see. So in that 3's, so how many 3's are there? 16 minus 3 plus 1. That's going to be 14 3's. So we don't need a 3. And if we do need a 4, and we do need a 6, we do need an 8, we do need a 10, we do need a 12. So we can see that we need all the even numbers, because so far there's just an odd number of even numbers. Like plain exponents, not counting like factorizations. So we know that m must include this stuff. But, so it's m, because we know that this times m times all these numbers times already a perfect square. Squared. So that must be a perfect square. So we can just eliminate perfect squares. That's a perfect square, so we can cancel that out. This is a perfect square. This is a perfect square. So 2 times 6 times 8 times 10 times 12 times 14 times m, that has to be a perfect square. But 2 times 8 is a perfect square, so we can cancel both of those out. Let's see, what else can we cancel out? So there's going to be a 6 into 6, so that turns into 2. And this 2 cancels itself out because that's 5. So then 5 times 14 times m is a perfect square. That's 70m. That means m is equal to 70. Because it's 70m must be a perfect square, and 70 is square free, which means that this m must be 70 because it's square free, so we can't eliminate it more. Okay, so that's problem 15, and the answer is C. So now let's move on to problem 16. Define an up no of a positive integer of 2 or more digits where the digits are strictly increasing, moving left to right. Similarly, define a down no to be a positive integer of 2 or more digits where the digits are strictly decreasing, moving left to right. For instance, 250 is an up no, and 8620 is a down no. Let u equal the total number of up no's and d equal the total number of down no's. What is the absolute value of u minus d? Okay, so let's just compute each of these by hand. Let's start with an up no. So what really is an up no? So let's just start with the case that the number is 2 digits. So let's see an example. 13. That works. 24. That also works. So what is this really saying? So it's strictly, so for every combination of 2 digits, you can always arrange them exactly one way to make it work. For example, let's just say you choose the 2 digits 7 and 9. You can always arrange it in exactly one way, 79. That's interesting. So is it just 10 choose 2 for the number of ways to choose 2? But no, because what if, let's take some special cases. What if you choose a 0, like 0 and 9? Then you'll get 0, 9. That's the way to arrange the digits to make an up no. But that doesn't work. So you can never choose a 0. The up no numbers can never have zeros. So instead, it's 9 choose 2, where you choose a positive digit. That's interesting. Now let's go to 9 choose 3. That's the case for 3 digits, and you can figure it out the exact same way. And you do ... all the way till 9 choose 9. Normally, they'd be 9 choose 10, but this number doesn't exist. 6, 7, 8, 9. Because there's a 0 at the front. So there's no 9 choose 10. So it's just this. From the cases from where there's 2 digits all the way until there's 9 digits. So what is that? Well, there's 2 ways of computing this. One way is computing by hand, but that's a little messy. So let's look for a better way. We know the combinatorial identity 9 choose 0 plus 9 choose 1 plus 9 choose 2 plus ... plus 9 choose 9 is equal to 2 to the power of 9, which is 512. Okay, but we're just asking for this. So just 512 minus 9 choose 0, which is 1, minus 9 choose 1, which is 9. So that's 502. Oh, so the number of up no's is 502. Let's try to do the same process to figure out the number of down no's. Okay, so same thing. Let's do casework. Case 1, it's 2 digits. So then, let's just start off what we did. We know that if we get like a group of digits, we can always arrange them to form exactly one down no. Except this time we can include zeros. For example, if we take the digit 0, 9, normally we can't form the up no 0, 9, but we can form the down no 9, 0. So it's just 10 choose 2, 10 choose 2. And then 3 would be 10 choose 3, and so on. So the number of down no's is equal to 10 choose 2 plus 10 choose 3, all the way until 10 choose 10. So from 10 choose 2 to 10 choose 10. So similar to before, we have the combinatorial identity 10 choose 0 plus 10 choose 1 plus and so on, all the way until 10 choose 10 is 2 to the power of 10 is equal to 1024. And now let's subtract out these two, which is 1 plus 10, which is 11. Which is 1024 minus 11, which is 1013. So the number of down no's is 1013. So the answer is just 1013 minus 502, which is 511. E. Just fill in that answer as well. Okay, so that was problem 16. Probably a slightly harder problem than 15. And now let's move on to problem 17. A rectangular box P has distinct edge lengths A, B, and C. The sum of the lengths of all 12 edges of P is 13. The sum of the areas of all 6 faces of P is 12/2, and the volume of P is 1/2. What is the length of the largest interior diagonal connecting 2 vertices of P? And again, the answers are all jumbled up. Okay, so the sum of all 12 edges of P is 13. That's strange. I thought there were only 3 edges. Aha, every single edge is counted 4 times. For example, if I quickly draw a rectangular prism, this edge, let's just say that's A, is counted 4 times. So it's 4 times A plus B plus C is equal to 13. And that makes sense because if all 3 edges are counted 4 times, then there's going to be 12 edges. Okay, so now A plus B plus C is equal to 13 over 4. The sum of the areas of all 6 faces of P is equal to 11/2. That's AB plus BC plus AC. And it's times 2 because, again, each face is counted 2 times. That's equal to 11/2. So then AB plus BC plus AC is equal to 11/4. That's actually all the information we need to solve this problem. So the volume of P is 1/2, doesn't matter at all, but let's just write it anyway, because you wouldn't have known that during the test. So what is the length of the largest interior diagonal connecting 2 vertices of P? That's just going to be the space diagonal, which is square root of A squared plus B squared plus C squared. We're just trying to find A squared plus B squared plus C squared. That looks similar to this thing squared. So let's try squaring that. We square and expand, we'll get this. And that's equal to 169 over 16. Aha! We can just plug this in. We'll get A squared plus B squared plus C squared plus 22 over 4 is equal to 169 over 16. Let's subtract this. So a squared plus b squared plus c squared is equal to 169 over 16 minus, now let's make this a common denominator, 88 over 16. That's 81 over 16. And the square root of 81 over 16? Well, that's 9/4, which is D. And just change the color to make it consistent. It's green. Okay, so that was problem 17. A pretty easy problem compared to 16 and 15, if you ask me. Okay, now let's go on to problem 18. Suppose that a, b, and c are positive integers such that a over 14 plus b over 15 is equal to c over 210. Which of the following statements are necessarily true? So let's just go through these statements one by one. If GCD of A14 is equal to 1, or GCD of B15 is equal to 1, or both, then GCD of C, 210 is equal to 1. So what this is saying is, so let's just try to find a contradiction to this to start off. And then if we can't find a contradiction, let's try to prove that it always holds true. Okay, so we know that for a contradiction, we know that if not both of these things are reversible, actually, if both of those, well, this statement, if GCD of A, 14 is equal to 1, or GCD of B, 15 is equal to 1, or both, that statement means, if that's true, then both of these fractions, or at least one of these fractions, is unsimplifiable. With that in mind, let's tackle this. Let's just quickly try to find an example, to get a better hold of what this problem is trying to ask us. So let's just say a is equal to 5. That's relatively prime. So that means that condition, 5 over 14 plus b over 15 is equal to c over 210. Now we know that since GCD of 5, 14 is equal to 1, we don't care about what GCD of b, 15 is equal to 1, because we just need one of those things to be true. Okay. With that in mind, let's go solve this. So b, we don't need that to be relatively prime with 15. So let's just make it b is equal to 6 or something. So let's simplify that. That's equal to 5 over 14 plus 2/5, which is equal to 70. It's going to be 25 plus 28. Aha, note that that has a denominator of something less than 210. And so the numerator and the denominator are not going to be relatively prime. So we just found a contradiction. We had this statement true and this statement not true. So I is false. Okay, so we can eliminate all answer choices with I. That's a lie. So we know out of these answer choices, I must hold true. So that's true. And we know that I implies I. Why? Because I is a more specific statement. It's saying if and only if. And this is saying or both. And this is saying both of them. So obviously it's going to be E. Because we know that I is true. And I implies I. So it's going to be E. So I'll just change the color to make it consistent. Green again. Okay, now on to problem 19. Okay, so this problem is about Sonia the frog, who chooses a point at random inside this square of side length of 6. And then she chooses a distance at random from 0 to 1 and a direction out of this set. And all her choices are independent. And then she hops in the chosen direction the amount. What is the probability that she lands outside the square? So let's break this up into some cases of where she initially lands. So, scroll to this. This is the first case that she lands inside this 4x4 square in the middle. And the next case is that she lands inside one of these corners. And the third case is if she lands on these edges. Obviously, if she lands in case 1, there's no way she can hop outside the square, because she can hop to here, but she can't hop outside the square. So that's eliminated. Okay, what about 2? So let's just say she's right here in 2. So what's the probability that she hops outside the square? So she has to choose one of 2 directions every single time. So that's a 1. So let's just first compute the chance that she lands in 2. This is a 1x1 square. That's just 1/9, because there's 4, because it has area 4, and this whole square has area 36. So that's 1/9. And there's a 1/2 chance that she chooses the right direction. But now that she lands in 2 and she chooses the right direction, what's the probability that she chooses this number to hop outside? That hops outside. Well, it's also going to be 1/2. Why? Because this point is anywhere. This length is x, this length is y, and x plus y is equal to 1. Just make that clear. That's x and that's y, where this is the point. So x plus y is equal to 1. So we know that it's a 1/2 chance because everything's random. So what's the probability that the number, so x and y, let's just take the number x. Let's just assume that she's hopping that way. That's the direction she chose, without loss of generality. So it's between 0 and 1, and that's the thing she hopped. And x is also between 0 and 1. So just the probability one of these is greater than the other, which is just 1/2. So the probability of going through the 2 is going to be 1/36. Now what's the probability of getting through the 3? So first of all, what's the probability of landing in 3? So it's just going to be 4/9. Because this is 4, this is 1. And so that has area 4, and these all have area 4. That's 16 total area over 36, which would just be 4/9. So let's just do the same process for the 3s that we did with the 2s. So there's a 1/4 chance that she heads in the right direction to start. And similarly earlier, there's a 1/2 chance that the distance she travels exceeds how far she is. So that's just going to be 1/18. The sum of these is 1/18 plus 1/36, which is 3/36, which is 1/12. B. To make that consistent, you can use green. So that's basically the end of this video. If you have any specific problem requests that you want to review, please comment below, and I'll try to cover that. See you guys next time. Also, please subscribe and leave a comment or like if you like this video.